let's talk about a few more examples of homomorphisms. So we saw a few examples already. So here's an example with the ring R being the group algebra. Okay, so recall that the group algebra of a finite group or the group ring of a finite group over a field K is, well, what was it? As a vector space, it had elements which look like 1 sub G. So these were the basis elements as G runs over the group G. So recall here I am taking G to be a finite group. So these form a basis of this space thought of as a vector space over K. But what's interesting here really is the ring structure. So we take 1G multiplied by 1H, we said is 1GH. Okay, so look back on the lectures on the group ring and so on to recall the definition. And let's do a specific case. Let's take G to be the group S3, the symmetric group, and K to be any field. So R is K of S3 in this case. So K is just any field here. So recall we had talked about a certain module for this group ring. What was that? The module M was, as an underlying abelian group, it was just a space K3 comprising column vectors x1, x2, x3, where xi's come from K. Okay, and so that's the underlying additive structure. That's the abelian group. In fact, it's also a vector space, but that's at the moment we think of it as an abelian group. And the action or the scalar multiplication by these basis elements 1 sigma, we had said, is given by the following formula. We can make this into, so recall M, so recall the following, that M is R module, and via the following definition, that the elements of the basis elements 1 sigmas, they act on this as follows. It maps it to a permutation of the 3 coordinates, and we had said you need to use sigma inverses there. Okay, and this is for all sigma in S3. Okay, so again look back on that lecture to recall how this became an R module and so on. It's a left R module. Now what we are going to do is to define a homomorphism of this space to itself. Okay, so let me take this space, this module K3, and let me define for you a homomorphism of K3 to itself. Okay, and the map is the following. Look at x1, x2, x3, the vector mapped to x1 plus x2 plus x3 in each of the 3 coordinates. So it just sums the 3 coordinates and places that value in each of them. Okay, so I claim that this map is actually a homomorphism. Okay, so let's check this. So claim F is R homomorphism, where R is the group ring. Okay, let's prove it. What do we need to do? We need to check that this is it satisfies the 2 axioms. So the additivity is easy. It's just easy to check. If I take a sum of 2 vectors, then the answer will be again a sum. So this is straightforward. I will leave it for you to check. Easy. But the key property we need to check really is the compatibility under scalar multiplication, that I can pull the R out for all x in K3. Okay, why is this possible? Well, let's take R to be these special elements, these basis elements 1 sub sigma, and let's check it for those. Okay, it turns out it's enough to check for those elements. So let's check for R equals 1 sigma. So on the one hand, I have f of 1 sigma acting on x. So my question is this the same as 1 sigma acting on fx? Okay, so I need to compute both sides and check that they are actually equal. So let's do that. So let's first compute the left hand side of this equation. So f of 1 sigma x. So what is this? Well, first I need to operate 1 sigma on x. Okay, and recall what 1 sigma does. So here's the action of 1 sigma. When 1 sigma acts on x1, x2, x3, it just permutes the 3 coordinates x1, x2, x3 in some way according to sigma. Okay, it's still the same 3 guys, but they occur in some other order. Okay, but observe that when I apply f to that answer, what is f doing? F is just summing up the 3 coordinates and giving me the total. Now if I permute the 3 coordinates and then I sum them up, well, that's the same as the sum is the same as the sum which I get without permuting the coordinates, right? It's the same answer anyway. So the left hand side is, well, it is x sigma inverse 1 plus x sigma inverse 2 plus x sigma inverse 3 in each component, but that's the same as just saying it's the sum x1, x2, x3. Well, let me just say multiplied by the vector 1, 1, 1. That's the same as this function f. Okay, so it's I can compute it like this. And now observe that what about the right hand side? So okay, I've computed the left hand side. The right hand side is, I'm supposed to take 1 sigma and I'm supposed to act it on the vector x1 plus x2 plus x3 in each component. x1 plus x2 plus x3, okay, in each component. Now what does 1 sigma do to this vector? Well, it again permutes the three components, but all 3 are equal to each other. So when I permute the 3, I don't get anything new, I just get the same answer again. Okay, so observe, because the 3 components are the same, it just gives me the same answer once more. It's just x1 plus x2 plus x3 on each component. Okay, and so that's exactly equal to the left hand side. Okay, observe, the left hand side was also the same thing. Okay, so we have checked it for things of the form 1 sigma, and again I leave it as an exercise for you to check that it's true more generally if I take my ring element to be sort of the more general form, linear combination. So this is all sigma in S3, C sigmas are all field elements. Okay, recall that's a typical element of my group algebra or group ring, and check that the same check for such ring elements as well, the most general ring elements, that the left hand side and right hand side will actually be equal. Okay, so that's the first example for this lecture, a homomorphism of a module over a group ring. Okay, now here's a second example. Let's look at another non-abelian group, the group of n cross a non-abelian ring, the ring of n cross n matrices over a field K. So let n be at least 2, K is any field. So this is the matrix ring, and recall again from one of our last lectures that we constructed a module for this ring, and the module was just again k to the n, which is all column vectors of size n. And what was the action? It was sort of the most obvious one. How does the ring R act on vectors from k to the n? So if I take an element of R, so in this case elements of R are nothing but matrices. So if I take a m in k and v in v, then how do I scalar multiply v with a? Well, the answer is you just multiply that matrix with that vector, it will again give you a column vector. That's the answer. Okay, so this is I'm just recalling for you the scalar multiplication on this module v, okay, by elements of R. So again v is an R module. Okay, so again look back on the previous lectures to recall precisely how this became a module and so on. But for now I am interested in trying to figure out what homomorphisms look like. Okay, so what do I want to do? I want to understand if f from v to v is a R homomorphism. Okay, then what can I say about f? What does that tell me about f? Okay, in other words, can I somehow characterize all homomorphisms from this module to itself. Okay, so let's again see what the consequences of this being a homomorphism would be. So observe for a start that I can do the following. Let me take A. So what is a homomorphism? Let's again recall its two properties: f of x plus y equals fx plus fy, fx plus fy for all xy in V, and f of property 2 Rfx for all x in my ring, which in this case is M and K. So let me try to understand what are all the various consequences of these two definitions. So in particular, let me start with this axiom 2 and take a special case. Let me take my R ring element to be the identity matrix, okay, or more generally let me take it to be lambda identity, where lambda is an element of the K and IV just denotes the identity matrix. Okay, so lambda times identity is the scalar diagonal matrix with all lambdas along the diagonal. So suppose I take this particular ring element and see what it implies. So I have f of Rx, okay, should be Rfx. Now what is f of Rx? Well, f of Rx by definition is I have to act lambda times identity on x. So this is f of the matrix lambda times identity multiplied with the vector x. So recall x now is a column vector here. Okay, the right hand side is, well, again I have to multiply the lambda identity with the column vector fx. Okay, so what does that mean? Well, this guy here is just if I multiply identity with x, I get back x. So this is just f of the column vector x multiplied by the scalar lambda. And the right hand side is again identity times fx, it will just give me fx again. So this is nothing but the scalar lambda times fx. Okay, so what do I conclude? Well, for these special matrices R, the scalar matrices, I conclude that f of lambda x must give me the same answer as lambda fx. Okay, and this should be true for all scalars lambda from the base field K. Okay, and this should sort of remind you of something that we did last time for another example. So we now look at the additivity property that we have, that was from the first axiom, together with this special property we have concluded. And what do these two things tell us? It tells us that if you think of V only as a vector space over K, then F is a linear transformation. So these two properties tell you that F is nothing but a linear operator on V. Okay, thought of as a vector space. So let me call it K linear operator. I'm only thinking of it as a K vector space. Okay, so first I've concluded it's a linear operator. Okay, good. But again, I haven't used the full force of my hypothesis. I know that f of Rx is Rfx for all R's, for all matrices. Thus far, I've only used R equals scalar matrices to make my first conclusion. Okay, so let's do it a little bit more generally. Let's use all R. So first, before that, observe f is a linear transformation. So what does a linear transformation or linear operator mean? So observe first, note f is a linear operator on the space of column vectors just means that f is given by multiplication by some matrix. Okay, so let's call it the matrix P maybe. Okay, if you wish, this is just a matrix of this linear operator with respect to the standard basis of Kn. Okay, so any linear operator always has a matrix, and in this case I take the standard basis, I compute the matrix of f with respect to the standard basis. Then of course the f evaluated on x is nothing but the matrix of f multiplied by the column vector x. Okay, so any linear operator is nothing but multiplication by a matrix P. Now the question is, what are the possible values of P, right? If I tell you what P is, I know what f is. So let me try and figure out if f is a homomorphism of R modules, what does it tell me about this matrix P? Okay. So now let's use the full force of the hypothesis. F of Rx is Rfx, this is known. Ring M and K, okay, which means what? So let me take, instead of R, let me call it A. Okay, so it's maybe better notation because psychologically I think of it as a matrix. So F of Ax should be A acting on f of x for all matrices A in M and K. Now what does this mean? I've just told you what F is, right? F is just multiplication by P. So this means in particular that if I take Ax and I multiply it by P, it should give me the same answer as A times Px for all A in M and K and for all column vectors x in K power n. Okay. Now what does that mean? Well, it's saying that the matrix PA and the matrix AP, okay, they give me the same answer when I multiply it by x for all x in Kn. Okay. This means in particular that the matrix PA has to be the same as the matrix AP, right? When I multiply it by every vector I get the same answer. That means those two matrices are actually equal. One way of seeing it is by multiplying it by the standard basis vectors, okay, that give you each column of the product. Okay, so I've concluded that P must commute with this matrix A, but it must commute with A for every A in M and K. In other words, this matrix P is extremely special. It commutes with every matrix, so this belongs to what's called the center of this ring. Okay, the center of a ring is just a set of elements of the ring which commute with all elements of the ring. Okay, so I conclude that this matrix P must actually belong to the center of this ring. Okay, and here's a little fact which maybe we will prove during one of the tutorials, is that the center of the ring of matrices, in other words the set of matrices which commute with all matrices, is nothing but the scalar matrices. These are the only ones which commute with all matrices, okay, set of all lambda in K. Okay, so what this means is that this matrix P is actually a scalar matrix. So what is that? What is this? I mean, for the moment accept this as a fact. So what conclusion do we make? We conclude then that the matrix P therefore must look like some scalar matrix. Therefore in particular this homomorphism F, which looks like multiplication by P, is just nothing but lambda times IVX. So this is just f of x. This homomorphism is just this very simple trivial homomorphism which is scaling by lambda. Okay. So what we concluded is that the only homomorphisms from Kn to Kn are the scaling homomorphisms, okay, the maps which send a vector x to some multiple of x. Okay, and that multiple lambda is of course some fixed. So for some fixed lambda for lambda in K. So if I choose different lambdas, of course I get different scaling operators. Okay, so those are exactly the set of all homomorphisms. So we have made the following conclusions: the set of all f from Kn to Kn such that f is R linear or is a homomorphism of M and K modules. So I want to think of this as a Kn as an M and K module. The set of all homomorphisms is just the set of all scaling maps. So this is just a set of all, so maybe we should call this scaling map something. So I fix a lambda, so maybe I'll call this f sub lambda, the scaling by lambda map. So this is just a set of all f sub lambda where lambda ranges over all elements of K. It's exactly the set of scaling maps. Okay, so that was a second example of what homomorphisms look like for this particular module over the matrix ring. Okay, now here's another interesting example, slightly more general, which is that suppose R is any ring, and recall that I can think of R as a module over itself. R is a module over itself with respect to this left multiplication action. So how does a ring element, what is the scalar multiplication on x? it just multiplies Rx. Okay, so this is the scalar multiplication operation. So this is the scalar multiplication. Okay, and addition is of course the usual addition on the ring. Now let's ask, when you think of R as a module over itself in this manner, what are homomorphisms from R to R? So I want to know, if F is a homomorphism, then what can I conclude about F? What sorts of possibilities are there? So let's again plug into the definition. A homomorphism means f of x plus y is fx plus fy for all xy in R. Property 2 says f of Rx is Rfx x in R. Okay. Now again, like we did before, so let's use the second property. That's the one which usually gives us something interesting and non-trivial. So let me take, in this case, let me just take x to be the identity element of the ring. Okay, so take x to just be the element 1 of the ring R, and now let's see what I get from that. So I get f of R scalar multiplying 1 should just be R times f of 1. Okay, and this should be true for all ring elements R in R. I fixed x to be 1 here. Now what does this mean? Well, this just means the left hand side is f of R, the right hand side is R times the element f of 1. So this is what I conclude. I've actually figured out what value my f has on the ring element R. The value is just R times this element f of 1. Okay, so f of 1 is some particular element of my my ring here. So let's call f of 1 as something. So let A be the element f of 1. So we'll just give this a name. Let's call it A. So then observe that this homomorphism f of R is just this following map, which is R mapping to R times A. Okay, so this is sometimes what's called the right multiplication by A. This is just the map which is right multiplication by the element A. Okay, so the beautiful thing here is that the homomorphisms from R to R, when you think of R as a left module over itself, so remember this is, I'm thinking of it as a left module over itself via the scalar multiplication, then the homomorphisms from R to R turn out to be right multiplication maps. Okay, it's all of this form where each element is multiplied on the right by some ring element. Whereas if you tried the same thing where, so let me leave this as a little exercise for you. Recall, I can also think of R as a right module over itself, as a right R module via the following thing. If I take a ring element x and I think of right action of R, this is just multiplying on the right. So this is a scalar multiplication now for all x in R, for all R in. Okay, when I multiply the element x by R, the scalar multiply, the answer is just x multiplied by R on the right. Okay, this makes R into a right R module. The addition is just still the usual addition. Then what do homomorphisms look like? Then f from R to R, homomorphisms are exactly of the following kind. It just takes a ring element f of R and multiplies on the left by some element A of the ring. F of R is this for some fixed element A in the ring R. Okay, so this is the left multiplication by A map. Okay, so when you think of R as a left module over itself, the homomorphisms turn out to be the right multiplication maps, and when you think of it as a right module over itself, the homomorphisms turn out to be left multiplication maps. Okay, and this is an interesting structure that comes up here, and that's something that we will take up again later on. Okay.